The world runs on data. Every email sent, every video streamed, every online transaction generates a small but constant pulse of heat. These digital activities are concentrated in vast, humming facilities known as data centers. Traditionally, these server farms are seen as enormous energy consumers, their primary byproduct being waste heat that must be vented into the atmosphere at great expense. The cost of cooling these digital engines is one of the largest operational expenses in the information economy. This reality has driven a global search for more efficient solutions, pushing engineers and architects to rethink the fundamental design of our digital infrastructure. What if this waste heat was not a problem to be solved, but a resource to be harvested? Imagine a different kind of data center. Instead of a sprawling warehouse on a remote plain, picture a cavern carved deep into ancient granite bedrock, hundreds of feet below a bustling city. This is not science fiction. It is a reality in Finland. In Helsinki, in Espoo, critical digital infrastructure is being placed deep underground. These subterranean facilities leverage the natural stability and coolness of the earth to operate with remarkable efficiency. Shielded from the weather, secure from physical threats, naturally insulated. This transforms the data center into something integrated and symbiotic with the urban environment. The most revolutionary aspect is what happens to the waste heat. In conventional data centers, massive air conditioning units expel heat, consuming vast amounts of electricity. In Finland's underground data centers, this heat is carefully captured, collected and upgraded using industrial-scale heat pumps, then fed directly into municipal district heating networks. Heat flows through pipes to warm homes, offices, public swimming pools. The digital furnace, hidden within the rock, becomes a source of clean, recycled heat for thousands, turning a global environmental challenge into a local, sustainable solution. We'll explore how Finland has positioned itself to pioneer this synergy between digital infrastructure and urban energy. A story where geology, engineering, and long-standing cultural practices converge. Finland's ancient granite bedrock makes these projects technically and economically superior. The core claim: Finland transforms data centers from energy liabilities into assets that help heat its cities. This introduction sets the stage for a deeper exploration. Finland's capacity for building these subterranean heat sources is not an accident. It's a consequence of its deep history, geological, cultural. The country rests upon the Fenno-Scandian Shield, one of the oldest and most stable granite formations on Earth. That bedrock provides an incredibly solid foundation for ambitious construction projects. For decades, Finnish cities have looked downwards for space. Car parks, shopping centers, energy plants, civil defense shelters. This long tradition cultivated world-class expertise in rock excavation and underground engineering. That pre-existing comfort with subterranean infrastructure created the perfect environment for the data center revolution. When the need for secure and efficient server farms grew, Finland didn't need to invent a new paradigm. It simply adapted an existing one. The same logic that made it practical to build a swimming pool inside a granite cavern also applied to housing racks of servers. The country already possessed necessary skills, regulatory frameworks, cultural acceptance. This readiness allowed smooth, rapid integration of data centers into the subterranean urban landscape, avoiding many of the logistical and legal hurdles other nations would face. The true genius lies in connecting these underground data centers to another established system: district heating. Much of Finland relies on extensive networks of insulated pipes that distribute centrally produced hot water. The system was designed for a cold climate. It was the missing piece. The waste heat from servers, while significant, is relatively low temperature. By itself, it's not hot enough for direct use in homes, but using efficient heat pumps changes that. A heat pump acts like a refrigerator in reverse. It lifts low-grade thermal energy to the high temperatures required by district heating networks. Suddenly, waste heat becomes a valuable commodity, we'll systematically unpack this integrated system. First, geological foundations that make underground construction viable. First, urban foundations, the existing underground networks in cities. Next, the thermal advantages granite caverns offer for cooling. Next, operational advantages like cooling. Next, and security. Following that, we'll detail capturing the waste heat. Following that, upgrading it with heat pumps. Following that, distributing it into district heating networks. Examples from Helsinki, examples from Espoo, Microsoft's pioneering projects. Finally, the economic factors that enable this model. Finally, the policy factors. We'll consider limitations and conclude that Finland provides a powerful blueprint for sustainable digital infrastructure. Finland's journey into subterranean infrastructure begins not with modern engineering, but with primordial geology. This shield is predominantly composed of granite and gneiss, rocks that were formed billions of years ago deep within the Earth's crust. Over eons, glaciers scraped away softer, younger layers of sediment and soil, exposing this incredibly hard and resilient bedrock at or near the surface across much of the country. This geological inheritance provides Finland with a foundation fundamentally different from most other nations, offering a platform of almost unparalleled strength and integrity. Unlike regions characterized by sedimentary rock, seismic activity, or deep soil deposits, Finland's bedrock is a monolithic constant. It is exceptionally dense, strong, and free from faults and fractures. The inherent strength of the granite allows for the excavation of enormous underground spaces without the risk of collapse or subsidence. This geological reality has profoundly shaped Finnish engineering and architecture. Where others might see an obstacle, a hard, unyielding mass of rock, Finnish planners and builders see an opportunity. Once a cavern is created, the rock itself becomes the primary structural support, minimizing the need for extensive and costly artificial reinforcements like steel beams or thick concrete linings. The stability of the Fennoscandian shield is not just a passive feature. It is an active enabler of ambitious projects, making the concept of building deep underground feasible, logical, and economically sound. Furthermore, the uniformity of this granite bedrock simplifies the planning and execution of subterranean works. Engineers can predict with a high degree of accuracy how the rock will behave during and after excavation. There are fewer geological surprises, such as unexpected water tables or pockets of unstable material, which can derail projects and inflate budgets elsewhere. This predictability reduces risk and streamlines the entire construction process, from initial surveys to final commissioning. Finland's geological gift is therefore a triple advantage. It offers immense strength, reduces the need for artificial supports, and provides a dependable medium for construction, setting the stage for its pioneering use of underground space. The process of creating a vast data hall hundreds of feet underground begins with modern rock excavation techniques where Finnish engineers excel. The primary method involves controlled drilling followed by blasting. Holes are drilled in a precise pattern into the granite face, then filled with carefully measured explosive charges. The detonation is meticulously timed to fracture rock predictably, allowing rubble to be removed efficiently. That refined technique creates massive, cathedral-like caverns with clean curved walls and ceilings, while minimizing vibrations and impact on the city above. Once cleared, the cavern's strength relies mostly on the granite itself. Arched ceilings are common, an engineering choice to distribute the overlying rock's weight into the walls. Vaulted ceilings are common, the same principle applies. Reinforcement usually comes from rock bolting. Workers drill long steel bolts deep and tension them, effectively knitting the rock together. Shotcrete is often sprayed to seal surfaces and stop small rock falls, but the native stone bears the load. This contrasts sharply with softer ground, where sedimentary rock, soil, or clay would require huge concrete or steel shells to hold back earth and water. Those shells are expensive, complex, and need constant monitoring for leaks and shifts. In Finland's granite, the cavern is self-supporting, lowering material costs and long-term risks. The scale of these spaces fits modern data centers. They need large open floor plans for long rows of server racks, extensive cooling systems, and power distribution units. Excavating halls hundreds of feet long and dozens of feet high without internal columns is a major advantage. That enables optimal layout flexibility, efficient airflow management, and easier maintenance access. Granite bedrock doesn't just permit underground construction, it enables ideal, stable, cavernous homes for our digital infrastructure beneath the city. Beyond its structural strength, granite possesses another crucial characteristic for subterranean infrastructure: low porosity and permeability. In simpler terms, the rock is incredibly dense and does not easily allow water to pass through it. While some fractures and fissures containing groundwater inevitably exist, the solid mass of the granite acts as a formidable natural barrier against water seepage. This is a critical advantage for any underground facility, but it is especially vital for a data center where the presence of moisture can be catastrophic. Water can cause short circuits, promote corrosion on sensitive electronic components, and foster the growth of mold, creating a hazardous environment for both equipment and personnel. In many parts of the world, building underground means waging a constant and costly battle against groundwater. Extensive and complex waterproofing systems are required to keep subterranean spaces dry: membranes, sealants, active pumping stations. These systems demand regular inspection and maintenance, and their failure can lead to disastrous flooding and operational shutdowns. In Finland's granite caverns, the need for such measures is drastically reduced. While some targeted grouting or sealing may be necessary to address specific fissures, the rock itself does the bulk of the waterproofing work. This inherent dryness significantly lowers both the initial construction cost and the long-term operational expense and risk of housing sensitive electronics deep underground. Another subtle but important benefit of the deep rock environment is its profound quietness and freedom from vibration. The sheer mass of the granite bedrock acts as a natural damper, absorbing and isolating the facility from the noise and tremors of the world above. The constant rumble of city traffic, the vibrations from nearby construction, or even minor seismic tremors are completely nullified hundreds of feet below the surface. This creates an exceptionally stable physical environment for the data center's hardware. High-density servers contain spinning hard drives and delicate cooling fans that are sensitive to external vibrations, which can reduce their lifespan and increase failure rates over time. This vibration-free sanctuary contributes directly to the reliability and longevity of the digital equipment. By minimizing physical stress on the hardware, the granite environment helps to lower maintenance requirements and replacement costs. It ensures that the precision-engineered components within each server can operate exactly as they were designed to, without the added wear and tear of a less stable setting. The combination of being naturally dry, quiet, and stable makes these granite caverns an almost perfect protective cocoon for the critical infrastructure of the information age. The rock provides a level of environmental control that would be incredibly expensive, if not impossible, to replicate in a surface-level building. Finland's ability to integrate data centers into its bedrock is as much about culture and urban planning as geology. For generations, Finns have recognized the potential beneath their feet. This isn't new. It's woven into their cities. Helsinki has an official underground master plan, a strategic guide for subterranean construction. The plan ensures tunnels and caverns are built logically, interconnected to avoid conflicts. The underground network is impressively extensive. Beneath Helsinki and Espoo lies a parallel city: underground shopping malls, bus stations, sports facilities, a modern art museum, Itäkeskus Swimming Hall, a full-sized complex in a bedrock cavern. Comprehensive civil defense shelters protect the whole population. This history created public acceptance and institutional knowledge. A mature local industry enables this. Contractors, engineers, geologists. They've honed safe, efficient hard rock excavation techniques over decades. Local know-how lowers risks and controls costs. Regulatory and permitting processes are clear and predictable. Companies building subterranean data centers follow a well-trodden path. When data needs grew, Finland extended tradition instead of starting from scratch. The Fennoscandian Shield's geological advantage was ready to be capitalized on. The foundation for underground data centers was laid long before the first server, built on a national legacy of looking down. One of the most significant operational advantages of placing data centers deep within Finland's granite bedrock is the naturally stable thermal environment. Hundreds of feet below the surface, the rock mass maintains a consistent temperature of approximately 6 to 8 degrees Celsius, 43 to 46 degrees Fahrenheit, throughout the year. This subterranean climate is entirely disconnected from the dramatic seasonal swings on the surface, from frigid Nordic winters to mild summers. For a data center, essentially a factory producing immense quantities of heat, this predictable coolness is an incredibly valuable asset. It provides a constant, low-temperature heat sink that can be leveraged for cooling, the single largest energy consumer in most data center operations. This natural coolness fundamentally changes the energy equation. On the surface, operators fight ambient air temperatures that can fluctuate by 30 degrees Celsius or more. They rely on powerful, energy-intensive mechanical chillers and air conditioning systems to maintain server temps around 20 to 25 degrees Celsius. Those systems can consume 30 to 40% of a data center's total power. Underground, the baseline is much closer to the desired state, dramatically reducing required energy. The granite itself acts as a massive thermal battery. Its volume and density absorb vast amounts of heat with negligible temperature increase. That buffer smooths short-term heat fluctuations from the servers. If there's a sudden computational spike, the surrounding rock passively absorbs excess heat, preventing rapid temperature rise in the data hall. Passive cooling reduces reliance on active systems, creating a more stable, predictable environment with less energy use. The constant cool simplifies cooling architecture. Instead of designing for wide external weather swings, engineers focus on a narrower set of thermal parameters. The challenge shifts to efficiently transferring server heat into the cool rock and into the heat recovery system. That deep rock advantage is the starting point for the remarkable energy efficiency these Finnish data centers achieve, turning major cost into a manageable, predictable engineering task. The stable, low temperatures of the granite caverns enable the widespread use of a highly efficient technique known as free cooling. This method utilizes the naturally cool ambient environment to chill the water used in the data center's cooling loops, bypassing the need for energy-hungry mechanical chillers for most of the year. In the Finnish underground context, water can be circulated through a heat exchanger that is cooled by the surrounding rock or by outside air during the colder months. This chilled water then flows through pipes to the data hall, where it absorbs heat from the servers via computer room air handler units. This process uses only the energy required for pumps and fans, a fraction of what a traditional refrigeration cycle needs. This approach leads to a dramatic improvement in the data center's power usage effectiveness, or PUE. PUE is a standard industry metric calculated by dividing the total power entering a data center by the power used by the IT equipment itself. A perfect PUE of 1.0 would mean that all energy is used for computation, with none spent on cooling, lighting, or power distribution losses. Conventional data centers often have PUEs of 1.5 or higher, meaning for every kilowatt used by servers, an additional half kilowatt is used for cooling and other overhead. The Finnish underground data centers, by leveraging free cooling and efficient heat recovery, can achieve PUEs as low as 1.15 to 1.2, placing them among the most energy-efficient facilities in the world. The operational reliability of the cooling system is also significantly enhanced. Mechanical chillers are complex pieces of machinery with many moving parts, making them a common point of failure in traditional data centers. A chiller failure can quickly lead to overheating and an emergency shutdown of IT equipment, resulting in costly downtime. The free cooling systems used in the underground caverns are far simpler and more robust. They rely primarily on pumps, fans, and heat exchangers, which have fewer failure modes and are easier to maintain. The massive thermal inertia of the surrounding granite also provides a crucial buffer, giving operators hours, rather than minutes, to respond to any issue in the cooling system before server temperatures reach critical levels. Ultimately, this efficiency translates directly into lower operational costs and a smaller environmental footprint. Every kilowatt-hour of electricity saved on cooling is a direct reduction in the facility's utility bill and its associated carbon emissions. For data center operators who work on tight margins and consume megawatts of power continuously, these savings are substantial. The geological advantage of the cool granite is thus converted into a tangible economic and environmental benefit, making the underground model not just a novelty, but a financially astute and sustainable choice for housing critical digital infrastructure in a cold climate. Beyond the thermal benefits, locating a data center deep within solid granite bedrock provides a level of physical security and resilience nearly impossible to replicate in a surface-level building. The hundreds of feet of overlying rock create a natural fortress, offering unparalleled protection against external threats. The facility is completely shielded from extreme weather events, tornadoes, hurricanes, floods, or heavy snow loads, which can damage or disrupt operations at conventional data centers. This inherent protection ensures operational continuity regardless of surface conditions. This subterranean location also provides exceptional protection against man-made hazards, both accidental and malicious. The granite mass can withstand the impact of explosions, fires, or vehicle collisions with no effect on operations below. This makes the data center highly resilient to industrial accidents or sabotage. Access is limited to a few highly controlled and reinforced entry points, far easier to secure than a sprawling surface campus with multiple windows and doors. This security by default is a major draw for clients who need to protect mission-critical data, such as governments, financial institutions, and healthcare providers. A subtle but crucial advantage is the natural electromagnetic shielding of the rock. The dense granite acts as a Faraday cage, blocking electromagnetic pulses and radio frequency interference. An EMP from a solar flare or from a malicious device could otherwise destroy sensitive electronics. A buried data center is naturally hardened against that threat. The rock also shields the facility from RFI, which can disrupt data transmission, and prevents the data center's emissions from being intercepted, protecting against electronic eavesdropping. These underground centers are often integrated with Finland's civil defense infrastructure. Many caverns are dual-purpose, designed as emergency shelters for urban populations. They are built to the highest standards of structural integrity and equipped with independent power, water, and air filtration systems. Co-locating critical infrastructure within this network ensures data assets are protected by the same measures that protect people, creating a unique synergy of national security and digital resilience. The operational advantages of the granite environment extend down to the health and lifespan of the individual pieces of IT equipment. The highly stable thermal conditions reduce thermal stress on electronic components. Materials expand and contract with changes in temperature. Over thousands of cycles, this can cause solder joint fatigue. It can create microfractures on circuit boards, and ultimately lead to premature hardware failure. By maintaining a near constant temperature within the data hall, the underground environment minimizes this wear and tear. That contributes to a longer, more reliable operational life for servers, for network switches, and for storage arrays. Furthermore, the deep rock location provides an exceptionally quiet, vibration-free setting. The massive granite bedrock effectively isolates the data center from surface vibrations, from traffic, heavy machinery, or even wind. This is particularly beneficial for mechanical components inside servers, most notably spinning hard disk drives and cooling fans. Vibrations can cause the read-write heads of an HDD to misalign, causing data errors and reduced performance. Over time, persistent vibration wears bearings in both hard drives and fans. That leads to increased failure rates and higher maintenance costs. The controlled dry environment also helps prevent corrosion and prevents dust accumulation. Two common enemies of electronic hardware. The air in the sealed underground facility is carefully filtered and dehumidified. In a surface building, dust can be drawn in from outside. Pollen can be drawn in as well. Those particles accumulate on heat sinks and impede airflow, which can cause overheating. Humidity can also promote corrosion on connectors and circuit boards. The pristine conditions within the granite cavern mitigate these risks, keeping cooling efficient and connections clean. Stable temperature, lack of vibration, clean air. These combine to create an almost ideal environment for high-performance electronics. That translates to lower hardware failure rates, reduced maintenance workloads for technicians, and a longer effective lifespan for expensive IT assets. Extending replacement cycles yields significant capital savings over the long term. The granite cavern is not just a secure shell. It actively helps preserve the health and functionality of the infrastructure it houses, contributing directly to the facility's overall reliability and economic viability. The process of turning digital computation into urban heating follows a clear and logical engineering chain. It begins at the most fundamental level, the server. Every microprocessor, memory chip, and power supply converts electrical energy into two things: useful computation and waste heat. This heat is an unavoidable byproduct of the physics of electronics. In a conventional data center, this thermal energy is treated as a nuisance, expelled to the atmosphere. In the Finnish underground model, this heat is recognized as a valuable raw material. The facility is designed around efficient capture. The first step is collecting heat directly from the servers. The most efficient method is liquid cooling. Instead of just blowing air across components, advanced data centers pipe coolant to server racks or to individual chips. This liquid absorbs thermal energy far better than air. The warm water, now carrying waste heat, is piped out of the data hall. Arrows from server racks to pipes carrying low-grade warm water, 35 degrees Celsius, to a central heat pump. This water is low-grade, between 30 and 40 degrees Celsius, 86 to 104 degrees Fahrenheit. It is warm but not hot enough for building radiators. This collected low-grade heat is the primary output. Goal: prevent dissipation into rock or venting away. The contained granite cavern keeps heat concentrated. Unlike surface buildings that lose heat, the underground space retains it. Warm water from the cooling loop is gathered and directed to the energy plant. Here, heat from thousands of servers is aggregated into a steady flow, ready for the next stage. This stage is about efficient collection and transport. Engineering focuses on maximizing recovered heat while minimizing energy use. Liquid cooling over air cooling captures heat in a denser, manageable medium. The entire layout is optimized: the arrangement of the server racks, the design of the plumbing. The server is no longer just a computer. It is the furnace at the heart of a larger energy system. And the first step is to capture every degree of its warmth. The warm water captured from the servers, while containing a significant amount of energy, is not hot enough to be useful for Finland's district heating systems. These municipal networks typically require water heated to between 80 and 120 degrees Celsius, 176 to 248 degrees Fahrenheit, to effectively warm buildings, especially during the harsh Nordic winters. The critical task, therefore, is to lift the temperature of the waste heat from its low-grade state to this high-grade, usable level. This transformation is accomplished using large, industrial-scale heat pumps. A heat pump is a remarkable device that functions like a refrigerator in reverse, moving thermal energy from a cooler source to a warmer destination. The process works through a thermodynamic cycle. The low-grade heat from the data center's water is used to evaporate a special refrigerant liquid, turning it into a gas. This gas is then passed into a compressor, which is the only major energy-consuming part of the system. The compressor, powered by electricity, dramatically increases the pressure of the gas, which in turn causes its temperature to rise significantly. This hot, high-pressure gas now contains both the original heat from the data center and the energy added by the compressor. It is now hot enough to be used for the district heating network, representing a major upgrade in thermal quality. The hot refrigerant gas is then passed through a second heat exchanger. On the other side of this exchanger flows the cold water returning from the city's district heating network. The intense heat from the refrigerant transfers to this water, raising its temperature to the required level for urban heating. As it gives up its heat, the refrigerant gas cools and condenses back into a liquid. This high-pressure liquid then passes through an expansion valve, where its pressure and temperature drop, returning it to its initial state, ready to begin the cycle all over again. This continuous process efficiently multiplies the value of the original waste heat. The efficiency of this system is remarkable. For every 1 unit of electrical energy consumed by the compressor, the heat pump can deliver 3 to 5 units of thermal energy to the district heating network. This is because it is not creating heat, but simply moving and concentrating it. This makes the recovered heat from the data center an incredibly energy-efficient source for the city. It leverages a waste product, applies a small amount of high-grade electrical energy, and produces a large amount of valuable, high-grade heat. In Finland's cold climate, where heat is a valuable commodity for more than half the year, this technology turns the data center's biggest liability into one of its most important assets. The theory of heat reuse becomes a powerful reality in Helsinki and in Espoo, where underground data centers are integrated with municipal energy systems. Helsinki's city-owned energy company, Helsinki, runs district heating and district cooling systems. Ouspensky Cathedral Data Center is a standout example, located in a former bomb shelter carved into granite beneath the landmark. Server heat from that facility is captured and fed into the district heating network, warming hundreds of nearby homes and offices. This is a two-way street. In winter, the data center supplies steady heat to the city. In summer, the economics flip. The same infrastructure provides cooling. The district cooling network uses cold seawater to supply chilled water to the data center and cool servers efficiently. The data center gets cheap, reliable cooling, and the city gets clean, recycled heat, reducing reliance on burning fossil fuels or on biomass. Espoo has scaled this up, leveraging waste heat from major commercial data centers to meet a large share of its heating demand. Investors include Solidium and pension fund Ilmarinen, backing data centers designed from day one for heat reuse. A single large data center can sometimes supply up to 40% of local district heating demand during peak operation. The model is scalable across cities. Success depends on a dense, pre-existing district heating pipe network, because building new distribution would be prohibitively expensive. Finland's long investment in centralized heating created the foundation, allowing heat from deep underground to be transported where it's needed, turning the city into an extension of the data center's cooling system. Section 4. The Microsoft Model. Designing for full heat recovery. Global technology giants are now embracing this Finnish model, with Microsoft leading the charge in designing data centers explicitly for 100% heat recovery. The company is developing a new data center region in southern Finland, in Helsinki and Espoo, From the very beginning, the core design principle has been the complete capture and reuse of all waste heat generated by its servers. This is a shift from retrofitting existing data centers to a heat reuse native approach. The facility is engineered as a dual-output power plant, one part providing computational power, the other providing thermal energy. Microsoft's plan shows economic and environmental viability. Microsoft has entered a long-term agreement with Fortum, supplying captured heat to Espoo, Kauniainen, and Kirkkonummi. Projected to be the largest single instance of waste heat recycling in the world. When fully operational, it will provide clean, carbon-free heat for an estimated 250,000 residents. This collaboration showcases a public-private partnership model for sustainable urban development. The scale enables big investment in heat recovery tech, optimizing every stage from the server chip to the city's heating pipes. The design ensures a reliable, consistent heat supply, making the data center a dependable part of the municipal energy grid. Reliability is crucial for utilities planning years ahead. Treating the data center as baseload heat lets Fortum cut emissions and operating costs, passing benefits to customers as more stable, eco-friendly heating. This initiative sets a new global standard for sustainable data center design. With the right geological conditions, a pre-existing district heating network, and collaborative planning, the digital economy can help decarbonize urban energy systems. The project moves beyond improving a data center's PUE to changing its role in the community. From isolated electricity consumer to integrated part of the local circular economy, turning a global waste stream into a local resource that keeps an entire region warm. Section 1. The economic calculus, costs versus savings. The decision to build a data center deep inside Granite Bedrock involves a complex economic calculation, weighing high upfront capital expenditures against long-term operational savings. The initial cost of excavating hard rock is substantial. It requires specialized machinery, skilled labor, and significant time to drill, blast, and remove thousands of tons of stone. These excavation costs can make the initial price tag for an underground facility higher than that of a comparable surface-level warehouse. This initial investment represents a significant hurdle and requires a long-term perspective from investors and operators, who must look beyond the immediate construction budget to the full life cycle cost of the facility over decades of operation. However, these high upfront costs are systematically offset by major savings in other areas. The need for structural reinforcement is dramatically reduced, as the granite itself provides the primary support, saving millions in steel and concrete. More importantly, the operational savings are immense and continuous. The largest saving comes from cooling. By leveraging naturally cool and stable rock temperatures, data centers can rely on free cooling for most of the year, drastically reducing electricity consumption. Cooling can account for up to 40% of a traditional data center's power bill, so these energy savings accumulate rapidly and improve profitability every day. The second major revenue stream is the sale of waste heat. In a conventional setup, waste heat is a costly liability. In the Finnish model, it becomes a marketable commodity. Operators can sign long-term contracts with municipal energy companies, creating a predictable, year-round revenue source from a byproduct that would otherwise be worthless. This income shortens the payback period for the initial investment. The economic equation is transformed. The data center is a service provider and a utility, generating value from digital and thermal outputs, diversifying its financial base. When all factors are considered, lower cooling costs, reduced security expenses, revenue from heat sales, and potentially longer hardware life, the life cycle economics of underground data centers in Finland become highly favorable. The initial high investment in excavation is repaid over time through substantially lower operational expenditures and new income streams. This makes the model attractive to long-term investors like pension funds and state-owned entities who prioritize stable, predictable returns over decades. In the right geological and regulatory environment, digging deep into the earth is a shrewd and sustainable financial strategy for the digital age. Section 2. Enabling policies. The role of planning and partnerships. The success of Finland's underground data center model is not solely geology and engineering. It's underpinned by deliberate, forward-thinking public policy. Municipal governments have played a crucial role. In Helsinki and Espoo, they've integrated data center development into official urban planning and energy strategies. They established clear zoning laws and master plans for subterranean construction, providing a predictable, streamlined regulatory pathway for investors. Proactive planning removes bureaucratic friction. It signals that projects are permitted and actively encouraged as part of the city's long-term vision. A key policy instrument: public-private partnerships between data center operators and municipally owned energy utilities. City governments broker the complex agreements governing the sale and purchase of waste heat. These contracts provide the financial certainty needed to invest in infrastructure like heat pumps and connection pipes. The energy utility gains a reliable, carbon-free source of heat to meet climate targets. The data center operator secures a long-term revenue stream. This symbiotic relationship stems from supportive municipal policies. National and regional policies incentivize heat reuse projects. Preferential electricity pricing for data centers that commit to heat recovery. Tax incentives for green investments. Grants for developing innovative energy-efficient technologies. By aligning energy and digital infrastructure policy, Finland creates a strong economic case for sustainable data centers. Data centers are viewed as integral components of the national energy system. This integrated approach ensures digital growth supports climate and energy goals. These enabling policies create fertile ground for investment and innovation. They provide stability, predictability, and financial incentives for large capital projects. The Finnish model shows policy is as important as hard granite bedrock. When municipalities and national governments act as partners, they steer private investment toward community benefits, resulting in economic development, digital growth, and urban sustainability, all mutually reinforcing through careful planning and strategic collaboration. Despite its remarkable success in Finland, the underground data center heat reuse model is not a universally applicable blueprint. Its viability is contingent on a rare convergence of specific conditions, the most important of which is geology. The model depends on having access to hard, stable, crystalline bedrock, like granite, at a shallow depth beneath urban centers. Many major cities are built on soft, sedimentary rock, clay, or sand, where excavating large, self-supporting caverns is infeasible or prohibitively expensive. In these locations, extensive, costly structural reinforcement would be required, erasing the economic advantages seen in Finland. The second limiting factor is climate. Finland's cold Nordic climate creates high heating demand for 6 to 8 months. In warmer climates, the market for low-grade waste heat is minimal. In Southern Europe, California, or Southeast Asia, the challenge is heat dissipation, not heat reuse. The massive investment in heat pumps and distribution networks would have no economic return. The third necessary component is a widespread district heating network. Finland and other Nordics have decades-old insulated pipe networks and central plants. That infrastructure is the essential channel to deliver captured data center heat. Most cities lack these systems and rely on individual furnaces or electric heaters. Building a new district heating network from scratch is monumental and extremely expensive. Therefore, scalability is geographically constrained to places with hard bedrock, cold climate, and established district heating systems. Parts of Sweden, Norway, or Canada might fit. But most of the United States, Asia, and Southern Europe are poor matches. While energy efficiency and heat reuse matter everywhere, the Finnish underground data center as heater is a brilliant but localized innovation. While the Finnish model offers numerous advantages, it is not without its own set of unique risks and long-term dependencies that require careful management. One primary technical challenge is the ongoing management of groundwater. Although the granite bedrock is low in permeability, it is not entirely impervious. Natural fissures and cracks in the rock can and do carry water, and the process of excavation can alter local hydrological patterns. Therefore, even in these dry caverns, a certain level of water management is necessary. This involves sealing fissures with grout and installing sump pumps as a failsafe. A failure in the system, though unlikely, could lead to localized flooding and equipment damage, requiring robust monitoring and maintenance protocols. Another long-term consideration is the thermal interaction between the data center and the surrounding rock mass. While the granite acts as a massive heat sink, it is not infinite. Over many years of continuous operation, the constant absorption of waste heat will slowly raise the temperature of the rock immediately surrounding the cavern. This effect, known as thermal saturation, could gradually reduce the efficiency of the free cooling systems that rely on the temperature differential. Must be modeled and planned for. Effective heat recovery is therefore not just an economic opportunity, but also a technical necessity to prevent long-term degradation by actively removing heat from the rock. The model also creates a critical dependency on the continuous operational load of the servers. The entire system, from the heat pumps to the municipal district heating contracts, is predicated on a stable and predictable supply of waste heat. If a data center were to significantly reduce its operations, relocate its servers, or shut down, the supply of heat would vanish. For an energy utility that has integrated this heat source into its long-term planning, this would create a significant shortfall that would need to be replaced, likely by burning more fossil fuels or biomass. This makes the long-term stability and financial health of the data center operator a matter of public energy security. These risks, groundwater ingress, long-term thermal saturation, and dependency on server loads, require a sophisticated approach to planning and risk management. The contracts between data center operators and energy utilities must include long-term commitments and contingencies to manage these interdependencies. The engineering designs must account for the slow changes in the geological environment over the facility's multi-decade lifespan. While the Granite Fortress provides immense security from external threats, it introduces a new class of internal, long-term operational challenges that must be understood and mitigated to ensure the model remains sustainable for generations to come. The story of Finland's underground data centers offers a powerful conclusion. By aligning modern technology with unique local advantages, it is possible to transform a global environmental problem into a practical local solution. The core argument rests on the convergence of four key elements. First, the nation's ancient granite bedrock provides a foundation that is strong, stable, cool, and dry, creating the perfect subterranean environment for sensitive digital hardware. Second, Finland's cold climate turns waste heat, a liability elsewhere, into a consistently valuable commodity. Third, long-established district heating networks provide the essential infrastructure to distribute this captured thermal energy to homes and businesses. Finally, institutional and cultural readiness enables these projects. Deep expertise in rock excavation, supportive public policies, and a history of underground urbanism, creating a low-friction environment for success. The combination makes the Finnish model technically possible, economically viable, and strategically brilliant. This integrated system is a new paradigm where the data center becomes a symbiotic partner in the urban ecosystem. The practical outcomes are clear, offering a model for other regions. Immediate result: dramatic improvement in energy efficiency, reflected in world-class PUE ratings. By leveraging the coolness of deep rock, facilities/electricity used for cooling a major operational expense. This translates to a lower carbon footprint and lower operating costs. Beyond efficiency, a new clean energy source for cities. Heat recovered from servers displaces the need to burn fossil fuels or biomass, contributing directly to decarbonization goals. A circular economy, digital energy recycled to warm the physical world. The model also boosts resilience and security for critical infrastructure. Nestled deep in solid granite, data centers are protected from almost all surface threats, from extreme weather to malicious attacks. That protection delivers unparalleled security for data that powers society and government. Finland turned geology into a strategic digital age asset. With intelligent planning and a holistic view of energy and infrastructure, digital demand need not conflict with environmental goals. Instead, they can be engineered to support one another. Final inspiring schematic. Electricity powers servers in a granite cavern. Waste heat is captured by heat pumps. Hot water flows into a city's district heating network, warming homes under a clean sky. Based on the success of the Finnish model, several clear policy recommendations emerge for regions with similar geology and climate. First and foremost, energy planning and digital infrastructure planning must be integrated. Municipal and national governments should actively identify locations where data center development can be co-located with district heating networks. Zoning laws and energy regulations should be updated to incentivize or mandate heat recovery for large-scale data facilities. This requires a shift in thinking, viewing data centers not just as IT projects but as components of the future energy grid, capable of providing grid-stabilizing services and clean heat. Second, public entities should support public-private partnerships to de-risk the initial investment. Facilitate long-term heat purchase agreements between data center operators and municipal utilities to provide financial certainty for both parties. Governments can provide grants for heat pump technology or streamline permitting for underground construction. Codify rules for building and operating subterranean infrastructure, as Helsinki did with its underground master plan, to provide clarity and predictability that attracts long-term investment from major tech companies and financial institutions. Pilot agreements to build trust and establish best practices. The digital economy keeps growing exponentially, so demand for data processing will increase. Steer that growth towards sustainable models to align expansion with climate targets. The Finnish example shows you can attract massive digital investment not with the cheapest power, but with the smartest, most sustainable energy ecosystem. Turn environmental constraints into economic opportunities to gain a competitive edge in the global tech race. The ultimate lesson from Finland is ingenious synergy. They leveraged ancient bedrock to solve a modern problem. Capture server heat, connect it to city heating needs, and you get a circular, resilient system. It's long-term thinking, where geological time meets the split-second digital age. Final takeaway: Finland turns geological advantage into practical energy and infrastructure solutions, using underground data centers to warm its cities.